Okay, I am recording. And I'll start out by sharing my browser with you. Okay, and as you can see, we're currently in week 12. Okay, and what we're doing here is just practicing for the exam, which you'll take online by Sunday, November 14th. Okay, so here's the practice exam that we're working on right now. We completed about five problems in it in class on Monday, and I'll try to be selective about the problems I work, because I know I asked some of you to please, look at this before class and pick out the problems you actually want to see me work out. Some of them are pretty straightforward. They're just applying like integration rules, but others are more word problems, and I know folks really prefer to see those worked out. So again, this is what I'm using as a document. When you do the exam, okay, here's exam 3. Remember, you can open it once when you get ready to start the exam. So please make sure you have everything you need when you are ready to start. You can use any of the resources in the class, any of the calculators. Again, I would refer you to the module that's below the final exam, called Online Tools for Math. Okay, it has a lot of the calculators gathered in one place. So that kind of makes it easy to find them. You don't have to search through the whole course for the calculators. And again, once you're done and you've submitted the exam, please take photos or create a PDF of your work, all right, and upload it to this assignment right here. Okay, that way I can regrade the exam and give you partial credit. Okay, your exam score will most likely go up from whatever you see in Canvas based on the work you upload. I'd also ask you to please complete this grade check. Let me know how you're doing, what you need help with. We've got about 4 weeks left in the course, 4.5 weeks, and I want to make sure we finish strong. So please, again, take the time to do the grade check. I know it's only 5 points, but it's an important way for us to communicate. I don't actually get to talk regularly with all of you, and I want to make sure that I meet your needs, that if you have something you need help with, you're getting the help you want. Okay, so anyway, give me a minute or so and I'll open up practice exam 3. What I'd like you to do in the meanwhile is pick the problems in the practice exam you want to see worked out. Okay, and again, put them in the chat. Okay, put them in the chat. Okay, we'll try to get to as many of them as I can, but again, I'll warn you, we're not going to be able to do all of them in an hour and 40 minutes. Okay, and that's not because they're so involved, it's because I talk too much. Okay, I try to explain as we go along. Okay, if you were actually doing these problems, you do them a lot faster. Okay, so don't let that worry you. All right, so while you're thinking, I'm going to open my notes. Let me share that with you. Okay. All right. So I'm seeing so far 10 and 11 and 14. Okay. Anybody else have any others they want to see? Okay, I'm going to wait a minute to give you all a chance to take a look at these, just in case you haven't gotten a chance to look at them yet. Okay. All right, we've got 19, 20. Okay, 13 and 14. I'll put 13. We've already got 14. Okay. Any others? You can see the ones in the list right at the top of the screen. As many as possible. Yeah, Alec, I agree. I'll be happy to show you as many as I can get in there. Okay, the one thing to realize about this exam is it kind of straddles differentiation and integration. So parts of the questions, like the beginning of the exam, or at least the beginning of the practice exam, has derivative questions. And then the rest of the exam is integration questions. So what's going to be important is that you're able to switch your focus and you realize, okay, that's a derivative. This one's an integral. Okay. All righty. Anyone still looking at the problems, trying to make a choice? Okay, I think I got everything anybody mentioned. Okay, which is 6 problems. Okay. So we ended off on Monday, for those of you who were in class, we ended off with number 5. Okay. When I upload my work for this, you're going to see every single problem worked out. Okay. So again, if you're going over the completed notes and you have questions about a problem we didn't do together, by all means, email me, ask me. Yes, even on Thursday. I know it's a holiday, but I'm assuming some of you will be doing work that day anyway. Just make sure you get any confusions cleared up, okay, before you take the exam. Okay, so again, all of the problems in the practice through problem 7, okay, are all derivative problems. Okay, this one, again, let me explain some of them before we actually jump in and do problems. Okay, like I said, we completed up through 5. In number 6, they're saying the volume of a cube is increasing at a certain rate. How fast is its surface area increasing when the length of an edge is 30 centimeters? Okay, this is a related rates problem, which involves implicit differentiation. So I'm just going to label it that way. Related rates. Okay, implicit differentiation with respect to time. So again, the way you do that is you come up with reasonable equations that relate things. In other words, they're giving you a volume. Volume of a cube is length times width times height. They're asking you about surface area. Okay, a cube has 6 square sides. Okay, and you can all find the area of a square. Okay, so basically, you're going to use those 2 equations, and then you're going to look for rates in terms of time, like how fast is the surface area changing with respect to time. So dA dt is something you'd be looking for here. Okay, so the setup to this problem is where all the thought goes. Okay, once you get it set up, it's not going to be hard to finish. Okay, number 7, we have a demand function and a cost function. Okay, remember they're basically saying if production of this profit is increasing at a rate of 50 units a week, find the change in profits. This is also related rates. And again, implicit differentiation with respect to time. I'm going to say R with respect to time. WRT with respect to. It saves me all the writing. Okay, and then what you need to do is you need to first build a revenue function. right? Which is going to be your price function. This should be a P of X. For some reason, I lost the P. Okay. So P of X times X. Okay. That's little p. And then your profit function is revenue minus cost. Okay. So you're going to build those. Okay. And then you're going to differentiate the profit function. Okay, so this requires a certain amount of setup as well. It infers you know how to build a revenue function from a price function, okay, and you know how to build a profit function from revenue and cost, okay? But other than that, they're both implicit differentiation problems. Okay, so again, looking at what you want to see, the first problem you want to see is number 10, okay? For 8 and 9, you're going to use the Riemann sum evaluator. Use Desmos Riemann sum calculator. Okay, please don't sit there drawing rectangles. Okay, use the Desmos Riemann sum calculator. There's a link to it in those online tools, in the online tools module. Okay, all right, find the actual area. So this is essentially, it says for 8 to 10, use this function, f of x equals x squared minus x between 0 and 2. Okay, so when they say find the actual area under the curve, okay, actual area using integration, okay, they say area is going to be a definite integral. What bounds do I put in the integral? Well, the ones they gave me, 0 to 2. Okay, and then the function is x squared minus x dx. Okay, so that's a definite integral. All right, and all I need to do in order to integrate it is use the power rule. Okay, so this is a simple integral. I'm just going to integrate it term by term. Okay, so remember how you use the power rule. You're going to add 1 to the exponent. So that's going to be x cubed. Put that over the new exponent. Okay, for the next term, the exponent is 1. I'm going to add 1 to the exponent, put it over the new exponent. All right, that's the integration. That's as simple as it is. Now we're going to evaluate that from 0 to 2. Okay, so here's where I use the fundamental theorem of calculus that says, how do I do this? I take my total function, my antiderivative, which is what this is, and I'm going to plug in 2 for x, and then I'm going to plug in 0 for x, and I'm going to subtract the 0 value from the 2 value. So set it up like this. Okay, conceptualize it. Upper bound minus lower bound. Okay, before you even put numbers in. Okay, get a big picture view of it. All right, so this is going to be 2 cubed over 3 minus 2 squared over 2. All I've done is I've plugged in my upper bound 2 here and here. Okay. And then what I'm going to do for the next part is I'm going to plug in my lower bound, which is 0, 0 cubed over 3 minus 0 squared over 2. Again, just to get an idea of what I did, here's the lower bound, and here's where it's plugged in to the antiderivative. Okay, now you can take your calculator and just enter this in, okay, the way it is, or you could take a minute and look at it and realize this second part, the second set of parentheses, this is 0 cubed, that's 0. 0 divided by 3 is still 0. Here's 0 squared, that's 0. 0 divided by 2 is still 0. This is 0 minus 0, which is 0. So this whole second set of parentheses becomes 0. Remember, I said that's usually the case when your antiderivative is a polynomial. Okay, and this is polynomial. Okay, please do not just assume a lower bound of 0 will give you a 0 value if you've got an exponential function. That won't be the case. Okay, so be very careful, but you can kind of cut down on your work by realizing this lower bound value is just 0. So all I need to do is evaluate it at the upper bound. Okay, I'm going to share some content with you. I'll share my calculator. All right, and then we can see that, turn it on. And that would just be 2. I can do it as a fraction, so I don't have to worry about what its value is. So 2 cubed over 3 minus 2 squared over 2. Okay, and again, that's 2/3. Okay, and if they want it as a decimal, you would round it to the appropriate places. Okay, just be a decimal, but the exact answer is 2/3. Okay, and again, I don't need this second half because I already determined its value is 0. Okay, anybody questions on 10? Questions on 10? Not seeing any. And go back and make sure I have 10, 11, 13, 14, 19, 20. All right, I want to make sure I get the ones you want to see.
In the
Okay.
beginning,
Yeah.
beginning, why is it 2 and 0? Like
Because what they said up here, if you take a
oh,
look at the directions up here, they said for problems 8 through 10,
okay.
use that function and that interval.
Okay. So I missed that. Thank you.
No worries. See, if I just had a function without without any bounds on it, the integral would probably be undefined because it would have an infinite area, right? So they got to give me a region they want me to find the area under. One other thing you need to pay attention to when you're integrating a function to find an area is you have to make sure when you look at the function that it's defined for all points between the integration bounds. Okay, this is a polynomial, so I don't need to worry about it being undefined anywhere. But if you've got x's and denominators, you want to make sure, like for example, that 0 isn't somewhere in this interval between the bounds. Otherwise, your area becomes infinite. Okay, you can't use the fundamental theorem when you've got undefined points between your integration bounds. Okay, there was a homework problem like that, and it was in the reading, but a couple of people missed that, and I want to make sure you're aware of that. I think we have a problem like that somewhere, and I'll point it out to you. Okay, so again, check the function before you just start integrating and make sure it's defined everywhere between the bounds. Okay, usually only a problem with square roots and with rational functions. Okay, let's take a look then at 11. That was another one you wanted to see. Okay, this looks complicated, but it's not. Okay, it says if the definite integral from 0 to 6 is 10, and the definite integral from 0 to 4 is 7, find the definite integral from 4 to 6. Okay, this is based on a concept in, it's actually a theorem of integration that says you can chunk up the intervals that you're interested in integrating between. In other words, if you take a look at these integrals, right, this one goes from 0 to 4. Okay, so this integral here goes from 0 to 4. Okay, this integral, the second one, the third one rather, goes from 4 to 6. Okay, and together, if you look at those, they go from 0 to 6. All right, and that's the same as this integral. Okay, so you can kind of add them up. Okay, so what I'm saying is there's a property that says the integral from 0 to 6 of f of x is equal to the sum of the other two, the integral from 0 to 4 plus the integral from 4 to 6. Okay, does that much make sense to everybody? Okay, I'm just piecing together the areas. You can think of the areas as having a seam at 4, okay? And if I sew together the area from 0 to 4 and the area from 4 to 6, I get the area from 0 to 6. These are the same function, f of x. Okay? Then all I have to do is put in the values they gave me. They said the integral from 0 to 6 of f of x is 10. The integral from 0 to 4 is 7. And they want me to find what the area is between 4 and 6. So I'll call that x. Okay, I think everybody can tell from looking at it, okay, that this area here, let me, rather than call it x, let me call it a so we don't get confused. Okay, you can see that a equals 3, right? Because 7 plus 3 would be 10. Okay, so a is 3. So I know the area under this function curve and between the x-axis from 4 to 6 has to be 3 because of this property. Okay, any questions on 11? So remember, you can add up integrals as long as there's no gaps. Okay. Any questions on 11? What happens when there's gaps? Okay, you really can't add up the sums. Okay, you can't add up the sums. And they won't give you one like that. Okay, you can't add up the sums. All right, anybody have any other questions? All right, so this is kind of like, again, thinking of, how you can integrate term by term. Well, it's the same idea with the definite integral, except what I'm saying is the end points of the intervals just connect to each other. Okay, I could even break up this 4 to 6 into 4 to 5 and then add 5 to 6. Okay, so you can break it into as many chunks as you need to. Okay, this is useful when you're finding areas and the function dips below x-axis. Okay, this is useful when you're trying to find areas and the function dips below the x-axis. If you find the x-intercept where that happens, you can break the integral into the part that's above the x-axis and find that area. And then the part that's below the x-axis, that's going to give you a negative area, remember, because y is negative down there. And you can just take its absolute value. Okay. In some cases, they'll want you to net out the areas. Okay. And if you're using a calculator, it will net out areas. But in some cases, if you're interested in total, like total distance traveled, you don't want negative areas. Okay, because remember we said displacement with a negative sign is just going backwards. Okay, that's still going to be distance traveled. Okay, so you want a positive value. All right, so part of it is reading the question carefully and deciding, does this area need to net out or does this area need to be positive and accumulated? Okay, depends on what it represents. Okay, and we'll look at more applied problems like that. Okay, let's look at the next one you wanted to see, which was number 13. Okay, number 13 is an indefinite integration problem. And again, the strategy with these problems is do some algebra first. And again, what you want to do is, let me put it in darker, something darker. So write this with exponents first. Okay, again, remember, if you see roots, you're going to try to write them with exponents first, because again, you want to be able to use the power rule because that's the easy one. All right, so what sort of exponent would be on y here? You tell me what exponent should be on y. Okay, we're taking a cube root of it and we're raising it to the 5th power. Okay, Miriam says 5/3. Anybody else have any ideas? Okay, Richard agrees. How about the rest of you? What do you think? Okay, 5/3 it is. Okay, why is that? Okay, thanks, Griffin. Remember, when you're looking at an exponent, okay, you have a power on top, right? And if there is a root, the root goes on the bottom. Okay, that's what a fractional exponent looks like. Okay, so here my power is 5. My root is 3. It's a cube root. Everybody see the 3 here? That's the index on the root. Okay, so what I want to actually do is take the integral of y to the 5/3 dy. Okay, now I can just use the power rule for integration, which says add 1 to the exponent, put that over the new exponent. And since it's an indefinite integral, no bounds, I need the plus c. I need the constant of integration. Don't forget that. All right, and then you can either take a fraction calculator or you can do it in your head if you remember that you can write 1 as 3/3, right? Okay, so if I write 1 as 3/3 and I'm adding 5/3, this becomes y to the 8/3 over 8/3 plus c. And again, that looks a little clunky, okay? And that's because I have a fraction in the denominator. So I'm just going to, instead of divide by 8/3, I'm going to multiply by the reciprocal. 3/8 y to the 8/3 plus c. Anybody questions on 13? Anybody questions on 13? Okay, nobody? Give you a half a minute to see if you got questions. Okay, let's take a look at 15. Okay. Anybody have any idea of what to do with 15 to make it simpler? What could you do to number 15 to make it simpler? Anybody? Remember, what's the tool for simplifying? Algebra. So I'm asking you, what can you do to this function algebraically to make it simpler?
Could we get u out of the denominator?
Absolutely. That's what you want to do, Gil. Okay.
Let's go.
Let's go. Okay, so let's do this. I'm going to start with your function inside, square root of u minus 2u squared over u. That's the function we're starting with. Let's rewrite that u, square root of u, as u to the 1/2 minus 2u squared all over u. Okay, and again, this is kind of the reverse of what you're used to doing. Remember, if you've got two fractions and they have the same denominator, you add or subtract them and put the answer over a common denominator. Well, this would be something like the result of that. You got these two things over a common denominator. That means you can split them apart again. So u to the 1/2 over u minus 2u squared over u. All right, and remember these u's down here have a 1 as an exponent. Okay, now you're in a situation where you can use the quotient rule for exponents to do the divides. Get rid of the denominators. Okay, how do I divide these? What do I do with the exponents? What happens with the exponents? Anybody have any thoughts?
You subtract the numerator exponent from the denominator one, right?
It's actually the other way around, denominator from
Ah.
numerator, but you're on the right track. All right, so here's the way I'm going to do it. U to the 1/2 minus 1 minus 2u squared 2 minus 1.
Yeah,
Okay,
that's what I meant. I just said it backwards.
that's okay. I do it all day long. Okay, so here's what it finally looks like. 1/2 minus 1 takes you to the negative side, right? And then this becomes 2 minus 1 is minus 2u to the first. Everybody good with that? All right, now you're ready to integrate from 1 to 9, but you got something much simpler to integrate. U to the minus 1/2 minus 2u to the first du. Okay, so this one required a fair amount of algebra up front to make it easy to do. Okay. It's really helpful if you start to view algebra as a friend rather than an adversary. Okay, especially when you're doing calculus and higher math. Okay, it does make things simpler. Okay. All right, so now I'm in a situation where I can use the power rule twice, once on each term. So let me do that. Okay, first I'm going to do the antiderivative. Okay, so I'm going to add 1 to the exponent. Plus 1. Put that over the new exponent. And this becomes 2u to the 1 plus 1 over 1 plus 1. All right, and then I'm going to evaluate that from 1 to 9. All right, so the rest of it is just, algebra. Okay. So this becomes, this first one, negative 1/2 plus 1 makes it 1/2 again. Okay, and this becomes minus 2u squared over 2. Okay, doing some more algebra. Okay, this gives me, okay, the divide by 1/2 over here is the same as multiplying by 2. Okay, and these 2's cancel. All right, so that's just some more algebra. And then I go from 1 to 9. All right, so now I'm finally to where I can use the fundamental theorem. Remember, that's going to be like this. Upper minus lower. Okay, and everywhere in the function rule, everywhere I see a u, I'm going to put the upper bound. So this would be a 9. Okay, so let me highlight that. So here's 9. Here's the first 9 that goes in. And this becomes minus 9 squared. Here's the second 9. And then for the lower bound, I'm going to put in the 1. Okay, so same function, 2 times 1 to the 1/2 minus 1 squared. All right, so there I'm putting in the upper and lower bounds. Again, all you need to do is bring up a calculator and type it in. Okay, you can use the exponent 1/2, or you can use square root if you remember that that's what it is. Hopefully by now you do. So this is 2 times 9. I'll do it just the way it looks. Okay, 9 to the 1/2 minus 9 squared. Now remember, this first set of parentheses, when you type it in a calculator, those are optional, okay? Because they're not really serving any function except in your own mind to group together what you're going to evaluate at the upper bound. But mathematically, they're not doing anything. The second set of parentheses, since it comes after a minus sign, you need those. Okay, so I'm going to put those in when I type it into the calculator. Okay, so 2 times 1 to the 1/2 minus 1 squared. Yes, I know you could do that in your head, but I'm just showing you can type it in the way it looks. Okay, and I got negative 76. Now, they did not ask me to interpret this as an area. They just asked me to evaluate the integral. All right, so that is a valid value. Okay. Anybody got questions on that one? Anybody questions on 14? Okay. No questions? All righty, the next one you wanted to see was 19. Okay. I reserve the right to go back to 18 and to 16 if we have time, and it looks like we will. Okay. So let's look at number 19. It says, given the graph of y equals x below, find the definite integral from 0 to 9 of f of x dx. Okay, just in case you can't tell, here's 9, here's 0. Okay, so what are they asking you to do? What are they asking for? What is the definite integral going to tell you from 0 to 9? Anybody, any ideas?
Be the area between
Yeah,
that under the line?
exactly, exactly. Notice they didn't give you a function rule, so you can't actually integrate anything, okay? The definite integral will give you the area between f of x and the x-axis between 0 and 9, between x equals 0 and 9. That's what the bounds are. The bounds are x's. Okay, so if you know that, okay, definite integral is a total value, or it's the area under a curve if it's a definite thing, okay? So let's take a look at this shape. What shape is that? Anybody know what that is? It's got two parallel sides. It's a four-sided shape with two parallel sides. Huh? Okay, it's called a trapezoid.
Dang it. I was gonna say that, but I thought I was wrong.
You got to be a little bit more,
I know, I
trust
know.
trust yourself.
I should have
Trust
said it.
yourself. Yeah, trust yourself. Okay, suppose you didn't remember it was a trapezoid. What else could you do? It's more work, but it'll give you the right answer. Anybody have any thoughts? Could you cut it up? How about if we cut it up into a triangle, another triangle, and a rectangle? Would that work? Yeah, sure it would. Okay, then you'd have to find the area of the left rectangle, the right rectangle, and at the right left triangle, the right triangle, and the rectangle in the middle, and add them all together. Okay, but it's easier if you have the formula for the area of a trapezoid. Okay, think of a trapezoid as a rectangle that got put in the wash and shrunk on one side. Okay, so instead of it having two nice equal bases, it has one base that's a little shorter than the other because it got shrunk. Okay, so if I want to find the area of it, normally a rectangle's area is base times height, right? Well, what I'm going to do here, since I have two different size bases, I'm going to average them. Okay, so think of it as 1/2, okay, the average of the bases, right? That's how you average something. You add them together, you divide by 2. So here's B1, here's B2, right? That's kind of the best I can do when I've got two different bases, all right? And then just multiply that by the height. All right, so it's the average of the bases times the height. Okay, it's not too hard to remember when you think of it that way. Think of it as a rectangle that got shrunk on one side. So I'm going to average the bases and then multiply by the height. Okay, so let's see if I can get these values. B1 looks like it's 3 units across, 1, 2, 3. And B2 looks like 1, 2, 3, 4, 5, 6, 7, 8, well, 9. Okay. All right, so now I'm just going to plug those values. The height of it, height, remember, is always a vertical distance. Okay, here it's between the two bases. Okay, so here my height is 1, 2, 3, 4 units. Okay, once I have all those values, my area is going to be 1/2 3 plus 9 times 4. Okay, 3 plus 9 is 12. Half of 12 is 6 times 4. So my area is 24 square units. Okay. Anybody questions on number 19? Anybody questions on 19? And remember, okay, when you're doing the exam, okay, you can use tools, right? If you need to look up the area formula for a trapezoid, it's okay. You're not taking the exam with a lockdown browser because I want you to be able to use the tools in the course. The one thing I want you to do is to make sure this is your own work. Okay, so the only thing you can't use is someone else's brain. All right, but you can use whatever tools you can find. Because again, in the real world, that's how it works. One little wrinkle in the real world is you have to make sure you find good tools, okay? Otherwise, bad tools can sometimes cause you more work than what you started with, okay? But that's a discussion for another day. Let's look at number 20, which was the last one you wanted to see. Okay, marginal cost for a certain product is given by, okay, and they give you a C prime number. Okay, so you know this is a rate. Right? A marginal or a derivative. Okay, this is a marginal or a derivative. Okay, so they tell you fixed costs are $1,400. Okay, now this is an important thing, fixed costs. Can somebody with, you know, accounting background or whatever tell me what's fixed cost? What does that mean? What's fixed cost? Somebody want to give it a shot? You don't have to give me the, you know, textbook accounting definition. In your own words. What are fixed costs? Nobody? Come on, guys. I know some of you are accounting majors. Okay, it means it's fixed. It doesn't change. Okay. It doesn't change with respect to what? In other words, do fixed costs depend on how many of the product you make? No. Okay. So another way of looking at it is these are your costs. Okay, and they're calling that's going to be C of X. Okay, not marginal cost, cost when X equals 0, right? So before I make any of my product, I'm in the hole for $1,400 because I probably bought equipment or something else that I need to make the product. Okay, but it doesn't depend, it doesn't change. As Richard said, it stays fixed. It doesn't change when X changes. That's the important thing. So when X is 0, the fixed costs are still 1,400. Okay? That's going to be important later. All right. Now, they're giving me a marginal cost and they want to know what are the total costs associated with production. What operation gives you total costs from marginal costs? What operation in this course? I realize there's a whole nother accounting procedure that doesn't involve calculus. Okay, but what operation here will give you total cost? Keywords total. Okay, what operation are we going to do, folks? Anybody have any thoughts? Well, we're starting with a derivative, so it can't be differentiation. There's really only one operation left. Okay? If you want to get a total function and you have a rate function, you're going to integrate it. Okay, that gives you a total. Okay, we really only have two basic operations in this brief calculus course. One is taking a total function and differentiating it to get a rate, like a marginal. And then the other operation is starting with a rate or a marginal and integrating it to get the total function back. Remember, they're sort of like inverse operations. They undo each other. Okay, so I want to integrate my cost function. Okay, they don't give me bounds. They're not asking me for a particular value of costs. They want a function. So it's an indefinite integral. Okay, everything is sort of, this is a linear function, so it's going to be easy to integrate. Somebody want to tell me what's the power of x associated with 28? Okay, so what's the power of x on the constant? What's the power of x on the constant 28? Anybody?
Would it be 0?
It's 0. Okay, x to the 0, remember, x to the 0 equals 1. Okay, x to the first equals x. So if you're seeing x's, you've got at least the power of 1. Okay, if you're seeing constants, your x power has to be 0. That might be helpful when we integrate. So I'm going to write it like this. Okay, x to the 0 is just 1. So all I'm doing is multiplying 28 by 1. Okay, and then I'm going to use the power rule. Okay, so by term, I'm just going to use the power rule for integration. Remember, this is a coefficient, so I just pull it through. Don't mess with it. And then with the x, I'm just going to say add 1 to the exponent, put it over the new exponent. The 28 has also become a coefficient, so pull it through. Add 1 to the exponent, put it over the new exponent. Okay, plus c. And this is going to be our total cost. No prime anymore, right? Everybody all right with that part? All right, the rest of it is just a little bit of algebra cleanup. This is going to be 0.02 x squared over 2. This is going to be 28x to the first over 1 plus c, which again I can write like this. Okay, now one more pass through the algebra. You can see 2 goes into negative 2/100ths, right? So this coefficient becomes that. Okay, and then 28x to the first over 1 is just 28x plus c. Everybody okay with that? Okay. Now, here we're saying fixed costs are $1,400. Okay, that means, right, since fixed cost okay, plug in 0 for x. Okay, 1,400 for c of x, and solve for c, the constant of integration. Okay, this is giving you another piece of information so you can get an exact value for the total cost function. Take a look at what they want to know next. What are the total costs associated with the production of 100 units? If I had C floating around in here, I couldn't answer this question because I don't know what C is. But they gave me this piece of information about fixed cost, saying, well, when X is 0, my fixed costs are $1,400. So I'll put in that for cost, and then I'll put in 0 for X. Okay, take a look at what happens. 0 squared is 0. 0 times negative 0.01 is still 0. 28 times 0 is 0. Both these terms drop out. And I get 1,400 equals C. So now I have an exact equation for my total cost, which is negative 0.01 x squared plus 28x plus 1,400. Okay, so specific equation. Because remember, when we did the antiderivative, we got a whole family of functions, okay? And this nailed it down to exactly one function. Everybody see what I did with the fixed cost? Yeah, everybody good with that? Okay, that's important. You'll usually be able to get another piece of information to do that. Right. Now I can answer their question is, what are the total costs associated with 100 units of production? That just says evaluate your total cost function when X is 100. Okay, so just plug that in. All right, bring up the calculator and just plug it in. Okay, so this is negative 0.01 times 100 squared plus 28 times 100 plus 1,400. All right, and I got $4,100. Okay. Anybody questions about number 20? Questions on 20? Okay. All righty. We're going to go back. Okay. Alec, it looks like you get your wish. We get to do as many as possible. So I'm going to go back to the first two on differentiation that we haven't finished, which were 6 and 7. Because I honestly think, whereas these are not hard, they're messy. Okay, I want to make sure people understand how to do these. Okay, so I'm going to need to erase what I've written here. Okay, because I don't have enough room to show you the work otherwise. Okay, so these are implicit differentiation problems. Okay, and they say, okay, got a cube and it's growing. Okay, the volume is expanding. Okay, so imagine I have this cube. Okay. And they're saying its volume is increasing at a rate of 10 cubic centimeters a minute. Well, it's a rate. Okay, so I'm going to write that as dV dt. The volume is changing with respect to time, and that's 10 cubic centimeters per minute. So that's one piece of information. And they're saying, how fast is the surface area increasing when the length of an edge, I'm going to call that side S, 30 centimeters. Right, that's the other piece of information they give me. Okay, and I need to basically try to figure out what's happening, okay, to the surface area. Before I do surface area, though, remember volume equals length times width times height. In this case, since it's a cube, that's S times S times S, or S cubed. Okay, so my volume is that. Okay, now again, surface area of this thing, if you think about it, it's got 6 sides like a die, and the area of each side is S squared. Okay, so it's 6 times S squared. That's the area. Okay. In order for me to do implicit differentiation on the surface area, okay, to find dA dt, Okay. I am going to need to know how fast the sides are increasing because I'm also going to need to differentiate S with respect to time. So I need ds dt. Okay. Okay. If you take a look at all of this over here with the volume, okay, I probably can get ds dt from that situation. So I'm going to start by differentiating volume first. Okay, so again, volume is a function of time. Okay, the derivative of v is 1. And then the derivative of the inside function that I don't know is dv dt. Okay, I don't have a function of volume in terms of t. Okay, so I just say dv dt. That's using the chain rule. Okay, now I have to differentiate s with respect to time. So I differentiate the outside, that gives me 3s squared. And then I differentiate the inside function, which is a function that's written in terms of t that I can't see. That's ds dt. Okay, so I've used the chain rule on the left, the chain rule on the right. Okay, now what I'm going to do is I'm going to put in all the information I have. I have dv dt, that's 10. Okay, I know s is 30. And I can solve for ds dt. Okay, solve for this. Because again, I'm going to need it when I differentiate with respect to t with the surface area. Okay, so this becomes 10. 30 squared is 900 times 3 is 2700. So 10 divided by 2700 is ds dt. And I think I figured that out. You could do it as 1 over 2700, or I did it as a decimal. Okay, and if you think about your units, the 10 was in terms of cubic centimeters a minute. Okay, and this is a squared centimeter value. So cubic centimeters per minute divided by squared centimeters gives you centimeters per minute, which is the right units. Okay, so all I did here was I differentiated v just to get ds dt. Okay, now I can actually spend time on what they wanted me to, which was to find out the rate at which surface area is increasing with respect to time. So I'm going to differentiate area with respect to time. Okay, if I differentiate the outside value of a, that's 1. Then this is dA dt. Okay, using the chain rule. Okay, I'm going to pull away the 6, and then I'm going to differentiate the s squared. That gives me, I'm going to basically say 2s. Okay, I'm differentiating here. And then the interior of the function is ds dt. Okay, everybody good with that? Okay, so here's what I have now. I have dA dt, which is what they want me to find, is 6 times 2 is 12. Plug in my S value, which is 30. Okay, and that'll be 30 centimeters. The ds dt is 0.0037, and that's centimeters per minute. So multiplying those units together is going to give me cubic centimeters per minute, which is what I want. I mean, square centimeters per minute, sorry. Centimeters times centimeters per minute is squared centimeters. per minute, which is an area rate of change. Okay, I'm just showing you how, even though I'm not writing in the units help you solve the problem. Okay, you're sure that you've got the units you want for your answer. Okay, an area rate of change is in square centimeters per minute. All right, so this is just a problem on the calculator. You just multiply all this together. Okay, and when I did that, I got dA dt equals 1.33 square centimeters per minute. Okay, so the area, okay, the surface area of the cube is increasing at like 1 1/3 square centimeters every minute. Okay. This is, I thought, a little more complicated because it's like in 2 steps. So I wanted to make sure you saw it. Any questions on number 6? Questions on 6? Okay, not seeing any. Okay, let's do 7. Because again, 7 is not hard. It's just multiple steps because you've got to do some setup to start with. All right, but it's also implicit differentiation. All right, so I'm going to start this by first figuring out my revenue function. So I said my revenue function is going to be price times the number I'm selling. Okay, so the price function they gave me is 0.24x minus 2 times x. All right, that's going to give me 0.24x squared minus 2x. Okay. The next thing I can do is I can find my profit function now. P of x equals R of x minus C of x. Okay, so my profit function is the revenue function I just found, 0.24x squared minus 2x. And again, remember when you've got a minus in your function rule, you need parentheses around the next bit, okay, to make sure you're distributing the minus. So the cost function they gave me was 890 plus 0.12x. Okay, so this minus sign is going to distribute to both of those terms, okay, which again you can do on a calculator. When you're done, you're going to have 2 terms with x in them. You'll have a negative 0.12x and a negative 2x. Okay, that's going to be negative 2.12x. So your profit function is going to be 0.24x squared minus 2.12x minus 890. Okay, just by distributing the negative sign and combining the like terms. All right, let's see what other stuff they gave us. They say the production of the product is increasing at a rate of 50 units per week. Okay, production of the product is increasing. Okay, find the rate of change of profits when x equals 1,000. Okay, so let me ask you, production is increasing at a rate of 50 units a week. What should I write that as? How should I write production is increasing at the rate of 50 units per week. How should I write that? What does that mean? It's a rate. How would I write it? What variable is tracking production? What variable is tracking production? And I'm really sorry if you can hear all the background noise. There are workmen next door chopping down trees. Sorry.
Yeah, I can't hear anything. You're good.
Okay, good. I'm so glad because it sounds really loud on my end. Okay, so what variable do you think is tracking production? Okay, I have an R of X, a P of X. What's production? Okay, well, this P here is price. Okay, so let me do some notation. Okay, this is price. This one is profit. Okay, this one's revenue. And we already had cost over here. So what's production or product? What is tracking the amount of product you're making and selling? This part's important, guys, because here's where you get stuck. Making and selling. Okay. Look at the way they worded it, guys. Production of this product is increasing at the rate of 50 units per week. What's tracking units? What's tracking units made? What variable? Yeah, X. Okay. So production increasing at the rate of 50 units a week, right? Per week is a time measurement. So this is dx dt equals 50. Okay, you've got to be able to read the problem and realize what rate are they giving me? Okay, they want to find rate of change of profits. That's D capital P dt. Okay, so they're giving you the fact that dx dt is equal to 50. They want dp dt. And that's good news because look at your profit equation. The only variable in it is x. And you're going to implicitly differentiate with respect to time. So you're going to need a dx dt, aren't you? Okay, so now let's implicitly differentiate. All right, so this side's going to be dp dt. Okay, it'll be p of x, derivative of the outside is 1, the inside is dp dt. Okay, every single term, since I'm doing a related rates problem here, is going to have a dx dt on it. So I differentiate the outside of this. Again, pull away the coefficient, differentiate 2x. The outside derivative is 2x. The inside derivative is dx dt. Okay. Do the same thing with the next term. All right. Pull away the coefficient. Bring down the exponent, 1. Drop the exponent by 1. Dx dt. Okay. And if I differentiate 890, what happens to the minus 890? What happens to minus 890 when I'm differentiating? It's a constant. What's the rate of change of a constant? It's a 0, right? So minus 0. Okay, now let's collect all of this, right? So the left-hand side is dp dt. This is 0.24 times 2, so that's 0.48x dx dt. Okay, here I have 212 times 1, that's 212. X to the 0 is a 1, so I don't need that. That's just times 1 times dx dt. Okay, and now what they want to know, find the rate of change of profits when X is 1,000. They're giving me an X value. Okay, I have a dx dt value, so I can evaluate this just by plugging it in. Okay, so this is just, plug in the numbers, dp dt. 0.48 times 1,000 times 50 minus 212 times 50. Again, this is strictly a calculator problem, but it's worth talking about what units it would be in. Okay, if you think about this, okay, this is a units number. Okay, this is also a rate of units per week. Okay, and profit is going to be basically in terms of dollars per week. Okay, so again, we're going to just plug in our numbers like this and put it in the calculator. Okay, so I just multiply all that out on my calculator, and I have 23,894. It's a profit rate of change, dollars per. Okay, so when I'm making 1,000 of these things and I'm increasing production at the rate of 50 units a week, my profit is increasing at a rate of $23,894 per week. Okay, questions on number 7? Questions on number 7? Okay, the implicit differentiation ones aren't hard, they're tedious. Okay, they're just tedious. And you need to keep track of what the rates are. Okay, I'm not seeing questions. Let's, there are a couple of the integration ones I wanted to show you, and I think that that'll be good for today. Okay, let me show you number 16. All right, again, Riemann sums, use the calculator. Okay, this one is a strict power rule over and over again, and then just evaluate it. Upper bounds minus lower bounds. That's not hard. Okay, this one, you're just going to rewrite this one as x to the 4th minus 6x to the minus 3, and then use the power rule. Okay, so that's not hard. Let's take a look at this one. Okay, let's look at number 16. How should I integrate number 16? How should I integrate number 16? Anybody have strategy? Okay, if you're thinking, well, I remember that e to the x is its own derivative and its own integral. So maybe it's just e to the 6x. And it's like, no, not quite. Okay, this is one where you need to use substitution. And why are you going to use substitution? Because you have a function in the exponent. Even if it's just some number times x. Okay. Now, if you're looking at that, you're saying, well, I thought you use substitution when you see a function and part of its derivative. Well, yes. Okay. The derivative of this exponent would just be 6. It doesn't give you a power of x. And remember, with substitution, you can play with the coefficients, right? So let me go through this. Okay, you're going to let u be 6x. Okay, so first you choose what your u is. And then I have to match everything else in the integral. I'm going to start by doing du dx. That's 6. Okay, I want to match a dx, so I'm just going to get the dx over there. Okay, and basically, if you take a look, you'll notice, aside from the 6x and the numerator, the exponent, there's no 6 as a coefficient. So I'm going to divide out that 6. So I just have dx. Okay. The other thing you want to remember is divide by 6 is the same thing as 1/6 du equals dx. I want to write it as a coefficient so I can pull it through the integration. Now I can do the substitution. Okay. I have the integral of e to the u. Okay. Now take a look. Here's what I did. Okay. I said u is 6x. All right. So now I have e to the u. And I also said 1/6 du equals dx. Okay, so I'm going to write that as 1/6 du. All right, so there's the substitution part. Everybody good so far? Right? Now what I'm going to do is I'm going to pull that, everything's multiplied, so I'm going to pull the 1/6 through the integration. And I just get e to the u du. Okay, and the integral of that is, guess what? E to the u du. E to the u without the du, sorry. Okay, so the integral of e to the u is e to the u, and I need the plus c. Okay, the last step is substitute x back. Right, and that gives me 1/6 e to the 6x plus c. Right? Anybody questions on 16? Okay, I wanted to make sure you got to see one substitution integral. Okay. Anybody questions on that? Let's briefly look at 17 and decide, can you simplify it? Look at 17. Can you simplify it before you start integrating? Anybody have a suggestion? Well, look at the powers on x. We did one like this before. How could you simplify this? Okay, you can use the quotient rule for exponents, right? Okay, first of all, 3 divided by 6 is 1/2. Okay, and then you could say x to the 1 minus 2. Right, so this is 1/2 x to the minus 1. Okay, or you could even write that as 1/2 1 over x. Right, there's one more power of x in the denominator than there is in the numerator. So now if you want to integrate from 1 to 4, 1/2 1 over x dx, you can pull through the 1/2. And then you have the integral of 1 over x dx. This is a special case integral. Remember, if I tried to add 1 to x to the minus 1, that would give me x to the 0 and I'd lose my x. So this is a special case. This gives you ln, the absolute value of x, 1 to 4. Okay? And this is just going to give you 1/2 ln 4 minus ln 1. And, if they want a numerical value, you just put it in the calculator and get an approximate value. But that's an exact answer. Okay, anybody questions on 17? Okay. Anybody questions? Okay, not seeing any. This is the last question. We've actually gotten to do them all, the ones that make sense to do by hand, okay? This is a true-false question. Now, what's important with true-false questions, of course, if you're doing it in an online test, it's either right or it's wrong. But you see this piece? Okay, explain your answer. Okay, so basically, in your notes, or if there is an explain box on the question that has to be manually graded, please don't leave it blank. I notice a lot of you when you're doing homework and it asks you for a reason, okay, and has it says, this will be manually graded by your instructor, you leave it blank. Don't do that. You're missing points. Okay, even, if it's a short explanation, explain why you decided what you did. All right, take a look at this function. Okay, it says the integral from -2 to 1 of 1 over x to the 4th dx equals 3/8. Do you think that's true or do you think that's false? Okay, let me ask you, what would you do to come up with an answer? What would you do to come up with an answer?
You could graph the function to see if there's any areas unidentified.
That's a great idea, Miriam. Let's try that. 1 over x to the 4th. All right, so here's my graphing calculator. Y equals 1 over x to the 4th. Okay, and that was from -2 to an upper bound of 1. Okay? Now, remember, the definite integral gives you the area under a curve. What do you think about that? will the area under this curve from x equals -2 to 1 be bounded? Okay, in other words, is it finite or does it go on forever? What do you think? I can do this a lot faster by doing this. Okay, there's your graph. I'm up to like 1600 already. What do you think? Is this area a finite number? Okay, a definite integral is asking you for an area. What do you think? Well, okay, you think it's a finite number. Anybody else have an opinion? Okay, look at the function rule. Okay, look at y equals 1 over x to the 4th. What happens when x is 0? Okay, so now I'm just asking you, don't look at the graph, look at this function rule and plug in 0 for x. What do you get? I like that. Okay. All right. So basically, once you plug in 0 for x down here, you get 1 over 0. 1 divided by 0 is undefined. Okay. There's a vertical asymptote. At x equals 0. The area under the graph becomes okay. Does everybody see this? What I was trying to show you in Desmos, this goes on forever, right? So the area between -2 and 1 is not a finite number, okay? What this was trying to show you, this problem over here, is you can't get a value for this integral, okay? So this integral is undefined when x equals 0. The fundamental theorem can't be used to find the area. Okay, so the answer here is false. Okay, it's false. And again, don't make the assumption if you see a question like this that it's always false. Okay, I'm sure you realized with more they randomize the values in the question. Okay, so actually look at the bounds on the integral. Okay, -2 to 1, and determine if this function is undefined anywhere in there. Okay, this function is undefined when x is 0. That's between -2 and 1. So this integral does not have a finite value. Okay, here's the reason. Okay, Since the function's undefined when x is 0, you can't use the fundamental theorem to find the area. Okay? Anybody questions on 18? That's our last one. Questions on 18? Anybody curiosity questions? Anybody got any other questions? I'm going to come back to the meeting and ask other questions on this material. Okay, any other questions?